Okay, so what we're going to see today, and this is going to kind of wrap up learning module 3, is that we're going to see how we're going to apply Kirchhoff's law to circuit analysis. By the way, we could go much deeper into circuit analysis techniques because there are many circuit analysis techniques. There's several. There's a mesh method, there's a node method, there's a superposition method. There's different methods to analyze circuits. We're not going to do that in this course because, as I mentioned before, in the case of you guys particularly, in 5th semester, you have a course called Industrial Electronics. And actually the first unit of that course is a unit that has to do with electrical circuits. So in that unit, the idea is for us to go deep in that unit. But we don't really need to take time here on that. Currently, if everything goes as should, I'm going to be teaching one class next semester, and I asked for the class to be the industrial electronics course for you guys. So hopefully, if everything goes well and we're able, that's going to be the class. So I'm going to be able to follow up on that. And the cool thing about that class is that it would be the first time we would teach that class under normal circumstances where we could actually go to the lab to do all of the lab exercises, which are actually cool. They're very cool lab exercises with sensors and stuff like that. So let's look at this circuit here. And remember what we've been doing, similar to what we were doing in the capacitance unit learning module. We have a circuit where we have elements in the circuit and we want to find the different variables of each of the elements. So when we were talking about capacitors, I know we had a capacitor array, we had power supply, and we wanted to find the total capacitance, the total voltage, the charges in each, the total charge, the charges in each capacitor, and the voltages in each capacitor. Well, now that we're working with resistors, it's very similar. We want to find the currents and voltages in the resistors. So in the previous examples that we had seen, we had a circuit with an array of resistors, and we only had one power supply, right? We only have one power supply. So it's very similar to the capacitance exercise. We just need to simplify the circuit, and we can find everything. However, what happens when we have more than one power supply in the circuit? Okay. If we have more than one power supply in the circuit, we're not going to be able to just calculate an equivalent resistance and go backwards in the analysis to do that. We can't do that. So we need to find alternative methods. And here is where Kirchhoff's law is coming in handy. So we've got the circuit that's shown here. Remember that we talked about certain concepts before. How many loops does that have? 3 loops, correct? Correct. And they're marked here actually. Okay. But remember that a loop is going to be a closed path within the circuit. So there's one loop marked as loop number 1. There's another box on the right that's marked loop number 2. By the way I put the arrows in the loops, it doesn't matter. I can really put them however I want. The arrows in a loop is just going to be a reference as to how I'm going to consider or analyze the current in the loop. I can set them up however I want. And there's a third loop, which is actually the whole path around the circuit. Okay, that's the one marked number 3. Imagine that this were a race. Imagine that this is a Mario Kart map. So there's three race tracks. Okay. Okay, good. How many meshes are in the circuit? Only 2. Only the 2 in the middle. The one at the outer edge is not a mesh because it contains loops within it. Okay, so the 1 and 2 are meshes. 3 is not a mesh. Okay, I'm just going to write that down here so it's in the recording and it's on the material. So
Why is it the last one considered a loop and not the other ones?
give me a moment. Again?
Why was the third one considered a loop and not the other one?
No, rather, why is the third one not a mesh? Oh, okay. So the definition of a mesh, there's no loops inside. So in the case of number 3, we've got loops inside number 3. And so that's why it's not a mesh. So one.
A mesh is a loop inside.
A mesh is a loop that doesn't have any loops inside. Okay,
So 1 and 2 are mesh.
correct. 1 and 2 are meshes. 3 is not a mesh because it's got loops inside it. So 1 and 2 are, I don't know if it's written meshes. I'm gonna write it like this. I don't think this is correct. I don't know if it's written meshes. Meshes, yeah, it would be meshes, I think.
It isn't also plural.
Like fish.
Like fish, yeah.
I'm not sure. Maybe, could be. That's a good observation.
It sounds like, but I'm not.
Mesh method. I'm gonna write it like this. I'm gonna write meshes. I like the meshes. 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 So 1 and 2 are meshes. Yeah. Just out of curiosity and to kind of help you reinforce your English. What do you? It is meshed with an E?
Yes.
Good, good. Google is our friend. What do we call a group of fish? We don't call them fishes. Well, we could call them fishes, but there's a specific name for a group of fish in English. A school. It's called a school of fish. It's called a school. Literally, like school. If you're talking about a school of fish, a group of 2 or more fishes is called a school of fish. What do you call a group of lions?
School
of well, in Spanish, but what would be the equivalent in English? No, because I'm saying this because in English, like they said, you said manada, and manada is a very specific word. Like school doesn't have anything to do with fish. In English, a group of lions is called a pride. That has nothing to do with lions. What do you call a group? And this is a real weird one. And it has to do with Game of Thrones, the names of the things in Game of Thrones. What do you call a group of crows?
Murder.
A murder. I don't know why. Crows is what would that be in Spanish? Cuervo. Cuervo. A group of crows, for some reason, is called a murder. Like murder, like killing. So a murder of crows. Yeah, I don't know where those things come from, but yeah. School of fish, pride of lions. They get together, right? Yeah. Yeah. Murder of crows. A Game of Thrones, a Clash of Swords, a Murder of Crows, etc. Okay, so what we're going to do is that the problem is asking us to find the current flowing in the 40 ohm resistor. Actually, what we're going to do is we're going to find all of the currents and voltages and all of the elements in the analysis we're going to do, because the analysis gives us everything. We can just select what we want, and we're going to use Kirchhoff's laws for that. And Kirchhoff's laws are basically, remember that there's 2 laws. There's the voltage law and there's the current law. The current law, which is the first Kirchhoff law, says that if I have a node, anything that goes in has to be equal to what comes out. So currents going in have to be equal to currents going out. Okay. The second law, which is Kirchhoff's voltage law, is that if I go around the loop, all of the voltages around the loop have to algebraically give me 0, or the voltage highs and the lows give me different values, and they have to balance each other out. So we're going to use those laws to find what we want to find in the circuit. Notice one thing here in the circuit. I'm going to mark it here. The circuit. Oh, do you want to ask them? Oh, okay. I heard a prompt. Notice that one thing we're going to do, this circuit is an example where they're giving us everything, but the way I'm going to draw the circuit in the other slide is basically the way it's going to be given in a problem where we only have the elements in the power supply. There's a lot of things already drawn, but notice that there are some arrows here. There are some arrows here, and these arrows are going to be important because these arrows are identifying currents. Current 1, current 2, and there's a current 3. Notice that each current is a part of a branch. Remember that we talked about a branch? A branch was a point that connected elements. Okay. So there's a current that's in this branch that I'm calling it I1. There's in loop 1. There's a current in loop 2 that's going in the part of the branch, and then there's a branch in the middle where there's resistor 3 and there's a current there. Okay, those are things that we are going to put in the circuit. Okay, I'm gonna switch over to the canvas view, to the whiteboard view, and I'm gonna redraw the circuit, and we're gonna see how we do the analysis. Okay. You're gonna join the Zoom? Okay. This is bless you. Oh no, by the way, I don't know if any of you or people you know about this, but the weather right now has been really weird. And there's something in the air because a lot of people have gotten sick from the weekend. Allergies, flu, and even stomach things. A lot of people have gotten sick from the on Saturday. My wife and my daughter went to a birthday party. They came back sick. I had class with my graduate group 2 days ago, and the same thing happened. We had a carne asada on Saturday, and my whole family got sick. Anybody that was outside on the weekend, there was something in the air.
A lot of people got rotavirus.
It's a rotavirus, yeah, the typical either stomach flu. This has been a terrible throat week. My throat is killing me. That's the Mexicali weather. It's just not cool. And if you got allergies, it's the worst.
Yes, I have allergies. I'm taking my
Terrible. The allergy medicines, I've taken every allergy medicines and they don't do anything to me. They've decided not to work. Allegra, like they say, that doesn't even tickle me. I can take a bunch of Allegra and my organism says, yeah, that's like Tic Tacs. For the nose, the Flonase, yeah. No, those stopped working with me years ago. Yeah, no.
But I forgot to buy it today.
That's the other thing. If you miss a dose, it's.
Yes, I sneeze.
Yeah, it's not. It's. Let's hope the weather. I'm sorry. Let's hope the weather gets better. That's a good question, Alejandro. For the purpose of a circuit analysis, you can draw them. You can draw them either way. Why? The correct symbol for a resistor is the one I just drew here. However, there's a concept that we're going to see further on, not in this course. That's the concept of impedance, which is a box that can be many things. It can be a resistor, an inductor, a capacitor. It can be a lot of things, but in the end, it has an ohms value. So that's why in some examples, instead of having the resistor symbol, there's a box. You can draw them either way. As long as you indicate when you're drawing the circuit that if it's a box, it's ohms, indicating that it's a resistor. Okay. In this version, I'm drawing it this way purposefully because this could be the way, the same problem I'm giving you. This could be the way I could give you the same problem with less of. Yeah, it's got a lot of. The other one has a lot of bunched up stuff. Yeah. This is V1 and it's 10 volts. Please help me out so I don't make a mistake in copying things. Yes.
Resistor 1 is 10 ohms.
10 ohms? No, it is an omega. It is an omega.
Then R2 is 20.
Okay.
And the other that one is 40. No. That one is 20 volts.
And this one
The
is
other
40, right?
resistor is 40.
Okay. Thank you. Thank you, Indra. Okay, so that's the circuit. Now we're going to do the circuit analysis. Now I'm going to go through the steps. And again, when you're doing the circuit analysis, try to follow the steps. If you just kind of follow the steps, you'll be good because it's very systematic. The process, and if we follow the steps and follow the conventions, it's really very direct how we apply Kirchhoff's law. So the first thing I'm going to do is that I'm gonna establish currents in the circuit. Yes.
Professor, which one is R2?
Oh, my 2 was too small here.
20 ohms.
Yeah, but the two was too little. There we go. That's a better 2.
Well, we need to consider the A and B.
Oh no, those are things that are in the.
Just consider that point by point to know the name.
No, that's a good observation, Estrella. This slide or the way this is drawn, everything is in the circuit. But imagine that when I'm giving you the problem, I'm actually going to give it to you like this. So one of the things you're going to do is say, okay, how many nodes? Let's just do this exercise to practice, because I might put that in the exam. How can somebody identify a node in that circuit? Where is a node? And you can tell me with regards to exactly. Let me. So for example, let's say that I give you this problem in the exam, and I say the first part of the problem, identify the nodes. So what you're going to do, which is already in the other slide, is that you're going to say, okay. So let me use colors here. I'm going to do it in pink. Yeah. So this is one node. What am I going? No, usually, and I want to stress the usually because this is not a standard. Usually, when we identify nodes, we use letters. That's not a standard that you're going to find in like a guidebook, but usually in circuit analysis, we use letters to identify nodes. We use numbers to identify meshes. Okay, so we can say, okay, this is one. Yeah, so it's not to confuse because there's 2 different analysis for nodes and meshes, and exactly it's not good. So this is going to be node A. Where's another node? This is another node. This is node B. So I'm just going to write it down here as a notation. The nodes are A and B. Let's say that's the first part of the problem I'm giving. And then the other part we already mentioned. Identify the loops, and I'm going to put those in purple. Identify the loops. Well, this is going to be loop 1. I'm going to say that this one here is loop 2, and I'm going to answer a question that might be on your guys' minds. Why are you putting the arrows like that? Can you put them the other way? Yes, you can. I'm just putting it like that. I'm going to explain a reasoning why, but if you do it the other way, it doesn't matter. You can do it clockwise or counterclockwise. It doesn't matter. And there's going to be another loop over here. And this one's called call 3. So these are the loops. 1, 2, and 3. And lastly, and I'm going to use, I don't know, let's use running out of colors I like. Let's use a brown. Oh no, we can use the same, just to identify that the meshes we already said are going to be 1 and 2. So in the other one, let's say we were already given that, but assume that I give you the circuit blank, you could identify those. Yeah. Okay. Now we've got those things here. So now what I'm going to do is I'm going to identify a series of currents in my circuit. And how am I going to identify the currents? I'm going to try to look at a branch or a point. Again, think about the racetrack. It starts here and it ends here. So in that branch, I'm going to establish a current. So for example, I'm going to say that we have a current here. And I'm going to call that current I1. By the way, in the original slide, it's yeah, I'm gonna do it like it's him, so it's not that confusing, but I'm gonna put it in uppercase. So I'm gonna call it I1. Okay. But by the way, so you guys don't get confused. I just drew I1 with a little arrow like that. Okay, but really I1 is going, if I'm gonna be really strict, I1 is going through this whole branch. Okay. Okay. Yeah, I'm drawing it like that just because I don't want to do so much. Oh, and why now I can answer the question. Notice that I drew the current in the same direction as the loop I drew. Now here comes the question. Well, why did in loop 1 I drew the loop 1 arrow? Why did I do it clockwise? Well, there's a reason I did it clockwise. And this is something that you can follow as a kind of guideline again. But if you do it the other way, it doesn't matter. You're going to get the same results. Because notice the 10-volt power supply. Okay, the 10-volt power supply has a polarity. We have a positive and a negative. Okay, a guideline I'm going to follow to do the loops and the currents is that the currents are going to try to go from positive to negative. Okay, so that's why in loop 1 I'm doing it. I'm doing it clockwise. By the way, again, if you do it the other way around, you're going to get the same results but with a different sign. That's the only thing. But it would not be incorrect. Okay. I'm going to draw another current, and I'm going to use loop 2, and this other current is going to go like this. Well, I'm going to draw it here on top. It's going to go like this, and I'm going to call this current I2. Notice that I'm following the same guideline. I'm going from, that's why in loop 2, it's counterclockwise because the power supply is drawn like that. So I'm going from positive to negative. Okay. And lastly, I've got a branch there in the middle. I'm going to draw a current there. And here's the question. Wait a minute. How do I draw that current? Do I draw it going down or up?
It's going down.
That's a good observation. Let me finish coughing and I will explain that. Sorry about that. Yes, that's a good observation, Estrella. Well, first off, I can draw it up or down. But Estrella just noticed, if I look at the two loops are coinciding in R3, and it seems the two of them are kind of like crashing and going down. Well, that's a good reference. So I'm going to draw it going down. Again, and I can't stress this enough, if you decided to do it pointing up, your analysis is still going to be correct. The only thing that's going to happen is if the arrows aren't the correct direction, the result is going to be negative. If all of these currents, I put them in the correct direction, all of the values are going to be positive. But if one of those currents is going in the direction that isn't correct, then that one is going to be negative. Okay? But the analysis is still going to be correct. I'm saying this because in your exercises or your exams, if you do it, let's say that Estrella and Alejandro are doing an exercise and they do it exactly like this. Okay? And then they say, no, I3 is going to go up. Okay? And then and Andrea say, well, no, I want this one to go clockwise. And then Juan and Jose Luis say, well, and this one I want to put it the other way around. If you do the analysis correctly, all of you are going to get the same values, just that some of the values are going to be in different signs. Okay, so don't worry that much about that. Like, you know, exactly. It's the same principle as in a force diagram. If you think the force is going one way, but after the analysis, the value is negative, It just means that it's going the other way. Is that correct? So questions with the currents. Okay, the next thing we're going to do is that we're going to apply Kirchhoff's laws. Okay, and let's start with the current law. Okay, Kirchhoff's current law. Writing is weird.
Professor, our other exam, about the third one was going to be next month.
No, not next week.
I thought you mentioned something that we're gonna finish.
No, we're gonna finish this, and after we finish this, same as the other one, you're gonna have a homework task with some exercises. I think we can do this exam maybe in a couple of weeks or after the second week of May. We don't have to rush it. We're gonna start a new topic next week, but that's not gonna be covered in the next exam, so we don't have to hurry it. No, it's not.
Just the exams and the final exam.
I think so. I'm gonna give you guys the option if you want to do a. No, yeah, this would be the third exam. I'm gonna give you guys an option if you want to do a fourth exam, or we just cover that in the final. We're gonna talk about that.
So
when we-
next week's exam will be the last one.
No, we're not gonna have an exam next. I don't, if I mentioned exam next week is not. No. We're not, let me recap, rephrase. We're gonna finish this topic today. You guys are gonna do some exercises. We're gonna start a new topic, a new learning module next week. This exam on Monday, when everybody's here, we're gonna set the date for the exam. It's not gonna be next week. We have enough time.
Make sure that the capacitor, the backpack is returning whatever we're ready.
Yeah, that's a good observation. Putting this, I moved the date, but
I remember you told us.
yeah, whenever you're ready, if you want to turn it in or test it, just let me know. Yeah, that's the idea. Yeah, just I want us to be coordinated because there's equipment in the lab and I need to see that it's available. So just we can coordinate that. Okay, so Kirchhoff's first law has to do with the sum of currents that are going in has to be the sum of currents that are going out in a node. So how many nodes do we have here? 2. So let's look at node A. What are the currents that are going into node A?
What are the what?
R1.
The currents.
I wanted.
I1 is going in. By the way, how do we know it's going in? The arrow has to be pointing toward it.
Okay.
So which are going in?
Just I1.
I1 is going in. I2 is also going in. And what is going out? I3.
Professor.
Yes.
I3 is the one in the
The what's in blue is kind of an explanation of Kirchhoff's current law. The sum of the currents going in is equal to the sum of the currents going out. The E is sum. So for node A, yes.
That E3, is it going like literally out? Or it's like looping?
No, I3 is just in this branch, just here. So I1 plus I2 is going to be equal to I3. Are we okay with that? And now let's look at node B. I'm going to do the complete step-by-step and detailed analysis, but in the end, when you guys do your exercises in the exam, you're going to notice that you can simplify this a lot, and you're just gonna you can just use what you need. If we yes,
Sorry.
go ahead.
You know, why I1 plus I2.
Oh, the first is, oh, we're gonna ask us, which are the currents that are going into the node?
Then we make an addition of those.
Yes, it's the sum of the ones that are going in is gonna be equal to the sum of the ones that are going out, the algebraic sum. Okay, now if we look at node B, what's going into node B?
I3.
I3, and what is going out of node? Uh-huh. Notice,
Teacher, but I have a question.
yes, it's the same equation.
Why are I1 and I2?
No. I always wait to see if the student can answer their own question. Is it clear? Okay. So let's go back to node B. I3 is going in and I1, remember that I1 and I2, these are extended. Okay, this means that they're going all around. So I1 and I2, is it clear that they're going out?
Yeah.
Okay. So are those two equations clear?
Yes.
Do we notice that they're the same equation?
Yes.
So
Has to be the same for equation?
it has to be if we're the equations have to be congruent, because again, this is the law of conservation of charge. So I can't have things going out and in one point and different things going out and in another point. So in the end, from this, I could have one equation that's I1 plus I2 minus I3 equals to 0. The only thing I'm doing is sending everything to one side. From these two, I have one equation. Okay. That's the application of Kirchhoff's current law, or law number 1. Okay. Now let's look at Kirchhoff's law. Oh, are you guys okay? Something spilled.
That's what matters.
What does it mean? KCL.
I'm sorry. Oh. KCL is Kirchhoff's current law, and KVL is Kirchhoff's voltage law.
That's the first step we need to do.
Uh-huh. So Kirchhoff's second law says that the voltages along a loop, the sum of the voltages along a loop are going to be 0. Okay. That, by the way, that implies that some things need to be negative and some things need to be positive, or else that mathematically isn't going to work. Yes.
I was picking up my stuff. What I did is ended up being 0. That is also the law.
In which one? In the blue?
first one.
The second one is not long.
Oh, what I'm writing in
The
blue,
first one.
in the first one,
Yes.
the red? Oh, the only thing I'm doing here in the red is that I've got the two equations for node A and node B. They're the same equation. I'm only sending the I3 to this side and the I3 to this side and making an equivalent equation.
Thank you.
Do we always have to have it 0? The next equation?
The thing is that what we're gonna get out of the end, Jose Luis, is we're gonna get to a system of 3. How many variables do we have here? I1, I2, and I3, those are my 3 variables. So if I want to solve for 3 variables, how many equations do I need? I need 3 equations. So in the end, we're going to get to a system of equations that we need to solve. So if we have it in this format, it's easier. Okay, so now the sum of the voltages in a loop is equal to 0. Okay, so let's look at, I'm going to look at loop 1. Okay, loop 1 is this box here. And we can start wherever we want. Okay, but I'm going to start here with the power supply. And what I'm going to do is that I'm going to follow the direction of the loop. Notice what I'm doing here?
Yes.
And I'm going to start here. And what's the first thing I find? Voltage 1. And In the case of a voltage source, it's going to have a polarity. So the arrow is going into the positive or the negative? The negative. So, oh, I'm going to say for loop, I'm going to use the purple here. For loop 1, the first thing I find is what? Minus V1, okay? I'm gonna write them down and then we're gonna substitute them. Minus V1. What's the next thing I find?
Plus.
The resistor. Now, there's no polarity in the resistor. So by default, I'm gonna think it's positive, okay? By default, since there's no polarity, I'm gonna think it's positive. And I'm just gonna write down right now, voltage of resistor 1, okay?
And how do we know there's no polarity? It needs to be.
Well, there is a polarity, but we don't know what it is yet because we don't know the directions of the currents. Okay.
So if it specifies a direction, it's gonna have.
Yeah, if the problem gives you in the resistor a positive and a negative, they're already telling you the polarity. But normally it's not going to give you that, so you're going to assume it's positive.
So the long line doesn't mean it's the positive. And the short line doesn't mean it's the negative.
No. Oh, in the power supply, yes. The power supply is always going to have a polarity. The power supply. The ones that don't have a polarity by default are the resistors.
Oh, okay.
Okay. The power supply, yes. The small line is negative. The long line is positive. Next up, what's the next thing we find in the loop? R3. So it's gonna. I don't know its polarity, so it's going to be VR3. And this is going to be equal to?
And 0.
0.
We're not considering the current.
Oh, not yet. Right now, right now I'm just writing the voltages, okay? But I want to leave everything in with regards to the current. So I'm going to rewrite this equation. So I'm going to say minus, I'm going to write it downwards here. What's the value of V1? It's 10 volts, right? Okay, bless you. It's 10 volts. Now, in the case of resistor 1, we don't know the voltage, but we have been working with the current. We know that the voltage in a resistor is the resistor multiplied by the current because of Ohm's law. So the voltage in resistor 1 is going to be equal to resistor 1 multiplied by current 1. No, those are the ones we're going to find. Okay. And lastly, the voltage in resistor 3 is going to be resistor 3 multiplied by current 3. And this is still equal to 0. I know the values of resistor 1 and resistor 3. Okay. Resistor 1 is 10 ohms. And resistor 3 is 40 ohms. Okay. Now, what am I going to do from all of this? In the end, what I'm going to get is the following. I'm going to remove the units for now because we can. And in the end, what am I going to have? Yes.
We're not going to consider 40 ohms.
Oh, I forgot the I3. Yes, thank you. I'm sorry, I forgot the I3. Boom, boom, boom. I3 equals to 0. I'm going to do this next step quicker. I'm gonna remove the units and I'm gonna organize the equation. And in the end, this is gonna be equal to 10 I1 plus 40 I3 equals to 10. Okay.
10 voltage.
Yeah, for this part, we can eliminate the units so the units don't confuse us. Okay, so we can eliminate the ohms and the volts because in the end we just want the equations. Okay, so it's not a problem if you eliminate the units. Okay, so this is going to be 10. I'm sorry. I1 plus 40 I3 equals to 10. Okay. Now let's do loop number 2. Well, we can't yet because we don't have enough equations. We've got 3 variables. We've got I1, I2, and I3.
Oh,
And
yes,
up-
yes, yes.
Up to this point, we only have 2 equations. We need at least 1 more equation to be able to do that. So now let's go to loop 2. And I'm going to start here. What's the first thing I find if I go like this? The negative V2. What's the next thing I find? R2, this is the voltage of R2 and the voltage of R3. And this is going to be equal to 0. I'm going to do the same thing I did before. V2 is minus 20 volts. The voltage in R2 is going to be 20 ohms multiplied by I2. And the voltage in R3 is going to be equal to 40 ohms multiplied by I3. And this is going to be equal to 0. Reorganizing, well, let me just do this. Oh, I pressed it too much. You couldn't do this with a normal whiteboard. R2 I2 plus R3 I3. Just want to be congruent with the procedure. Minus 20 volts plus 20 ohms I2 plus 40 ohms I3 equals to 0. And organizing these, in the end, I'm going to have 20 I2 plus 40 I3 equals to 20.
If, for example, in the middle branch, there was 2 resistors in series,
Mhm.
we would use resistor 4 times current 3.
It's the current that's going through the resistor, correct. If we had 2 or more resistors in the same branch, we would use the current that's going through that resistor. That's correct. By the way, let's try to simplify this even more. Is there a way that I can make this a little bit more simpler?
You can divide it all
By
10.
By 10, this would be then I1 plus 4 I3 equals to 1. Divided by, and this one, we could do exactly the same thing. And we would have 2 I2, I'm sorry, by 20, correct. This would be I2 plus 2 I3 equals to 2. I'm-
No, because we are dividing.
By
it
20, yes, correct. I'm going to do loop 3. We really don't need loop 3. We've already got 3 equations. We don't need loop 3, but I'm just going to do it so we can practice. But we don't really need loop 3, but let's do it. If we look at loop 3, yes, loop 3 is a loop that's going all around. Okay, so let's start off here. The first thing we find is minus V1.
Teacher, you said you were not supposed to do those 3, or is that necessary?
No, it's not necessary. I'm doing it just so we can practice, but we really don't need it because we already have the 3 equations we need. However, in loop 3, we're going to get a 4th equation. We don't need it, but we could have done loop 1 and loop 3 or loop 2 and loop 3. As long as we get 3 equations, those are the analysis we need. I'm just going to do it so we can practice. We've got voltage 1, which is, then we've got resistor 1, the voltage in resistor 1. Then we're going to have the voltage in resistor 2. Yes.
But the voltage, there is positive. No, V1.
In which one? In V1?
Yes, that one. Or how are we considering? the
Oh,
second?
we're considering the arrow.
Okay.
Yeah, so even if I draw it from that point, we're considering where the arrow goes in. No need to be, sorry.
We need to start always from the voltage one.
No, you could have started in voltage 2 and you're gonna get the same equation, as long as you go around the loop. Okay,
But the loop there is impossible, right?
in which one?
In the third loop.
Here?
There,
Oh, yes, this is positive. Yes, this is going in.
But the. Yeah. Professor, so first, for example, loop 3,
Mhm.
we first have to go to V1.
Oh, I started in V1, but we could have started here in the. Okay, let's, so the loop 3 is this loop here. Okay, so what I'm gonna do, and I'm gonna erase it because I don't want, but actually this is the complete loop. And so imagine that the loop has these arrows. This is the loop. So where the arrow or the flow, where is it going in? Here. You see that?
Yeah.
So it's going in to the negative.
But you can say that it goes in to positive.
Yes.
That's why she had a positive.
Yeah, that's why V2 is positive.
Okay.
Yeah. So you're gonna, in the case of the power supplies, you're gonna put the sign where it goes in. In the case of a resistors, they're all gonna be positive. Okay. Okay. And in this case, we're gonna say that minus 10. Yes, minus 10 volts plus R1 I1 plus R2 I2 plus 20 volts equals to 0, minus 10 volts plus 10 ohms I1 plus 20 ohms I2 plus 20 volts equals to 0. This is going to give us minus 10 plus 20 is going to be 10. So this is going to be equal to, I'm going to simplify the equation. This simplified is going to give us 10 I1 plus 20 I2, and 20 minus 10 is 10. And when I send it to the other side, it's going to be negative 10. And I can divide everything by 10, and this can also be converted into I1 plus 2 I2 minus 1.
This part.
No, we're actually already done. In a way, and let me explain why.
That's all we need to do.
This is basically it for Kirchhoff's laws. Basically, what's happening here is the following: we have three currents, I1, I2, and I3, and we need 3 equations because we have 3 variables. So actually, we have 4 equations here. We can use whichever combination of 3 we want. So let's call this equation 1. This is equation 2, and this is equation 3, and this one is equation 4. We can use any of these equations to find the solution. We just need 3. Yes.
Are we going to be seeing combined resistors? I mean, combined circuits that have resistors, capacitors?
Not in this course. That's in industrial electronics. That's what I was mentioning to Alejandra when she asked about the boxes. A combination of a resistor or an inductor or a capacitor, that's another concept that's called impedance. And that applies more to AC circuits. We're going to see that next semester. That's not contemplated here. Well, it could be contemplated here, but I find it redundant to see it here and take too much time on that if we're also going to see it next semester. So actually in the exam, by the way, in the exam, this is what I'm going to ask you to do. Actually, since these are systems of equations, I'm, even if I say it this way, it's going to sound weird, but I'm really not interested in you demonstrating to me if you know how to solve a system of equations. I'm going to assume you do, but that's going to take a lot of time, and you might make mistakes there. What I need you to do is to do the analysis correctly. So actually in the exam, this is what I'm going to ask you to do. It's going to be I'm going to give you a circuit and say, identify the nodes, identify the meshes, identify the loops. Find the system of equations that's going to find the currents. And these are what you're going to give me. By the way, again, we didn't need to do the analysis of loops. By the way, what is redundant in this exercise? Yes, we didn't need to do loop 3. And we could have just done one node. Okay, and it's correct. I'm doing it completely so we can find it. Now, in the exercises of the homework test, I am going to ask you to calculate the values so you practice. But there's 2 ways you can do this. You can actually solve the equations, and you know how to solve equations. Or there are web pages that can do that. And actually, let me see if I can find one here. But there are some web pages where we can that can help us out. Actually, I don't remember if I have it in the. No, I don't have it. I don't have it in the PowerPoint, but there are some web pages. Let me see if I can find one. Google, help me out in Google. Yes. Yes. System of equations solver. And there's a bunch of them there. Systems of, I'm not sharing this on the screen with the systems of equations solvers. There's a bunch of them there. So I don't know, I'm gonna grab the first one. There's a few that, oh, this is the one I've usually used. I think so. I think it's the one I've used. This, these tell you, is it a 2 variable, 3 variable, 4 variable? This is a 3 equation, so we can use that one. Oh, what did I do there? Oh, here are the 3 equations. So I'm literally going to write them down here. And actually, these softwares, you can actually put the variables there. So I'm gonna, where is the, let me just switch over here. So let's see, first equation is I1 plus I2 minus I3 equals to 0. Okay, so I1 plus I2 minus I3 equals to 0. That would be the first one. Let's see the other equation here. We've got I1 plus 4I3 equals to 1. I1 plus 4I3 equals to 1. Oh, I don't know if I have to put the multiplication. No, actually, no. I think I'm going to confuse the. I think I'm going to confuse the equation solver. I'm just because I don't want to mess this. I'm going to call them X, Y, and Z because I think if I put I1, I2, it's going to think it's a coefficient. So it's going to be X plus Y. X plus Y minus Z equals 0. And here it's going to be X plus 4y equals 1. And this one, and the last one, excuse me? Z, right? Yeah, because it's the third one. Yeah, thank you, Alejandro. And the last one would be I2 plus 2I3 equals 1. So it would be Y plus 2Z equals 1. Let's see what it gives us. So these are this would be the solutions. Okay, this would be the values of the currents. I'm going to write them down in the other. So solving I1. I'm going to write that down over here in green. So I'm going to write them down for another color. These are going to be the solutions. Horrible, horrible box. So solving 1, 2, and 3. Solving. You think it's cold in the classroom? Yeah. Solving 1, 2, and 3, we get that I1 is equal to minus 1/7. Can somebody calculate 1 divided by 7? How much that is? Please. 1/7. 0.1428. Yep. Okay. Now these are amps. 0.1428 amps. Remember that values for current should be small. That's and it's negative, which is important, and we'll talk about that in a moment. Amps. Then I2 is equal to 3/7. Can somebody calculate that, please? 3 times that. 0.4285 amps. And lastly, I3 is going to be equal to 2/7 amps. 0.2857. So the original problem, what did the original problem say? The original problem said, find the current flowing through in the 40 ohm resistor. Which is the current flowing in the 40 ohm resistor? It is I3. This is actually what specifically the problem is asking us about. But we found all of the currents. Now, one of the currents is negative. Which current is negative? I1. That only means that I1, instead of going this way, it's actually going this way. It just means that the current is going the other way. And that can happen. Okay, it just means that it's going the other way around in reality. Okay. And that would be the complete analysis. I have never in my whole career as a professor had such colorful notes to my classes before the pandemic. No, before if I would have had to do this in the whiteboard, it would have been all black and my writing would have been much worse than this.
I think that method, like instead of the board, like allows us to follow up.
I'm gonna say something that might be controversial to some professors. Bless you. But I know that the whiteboard is something that a lot of professors like to use. And if you can use the whiteboard kind of like this and use a lot of colors and you have good writing, which I know some of my colleagues do, then it's great. But I really prefer this because it's actually being recorded and I can take a screenshot and put it in the PowerPoint. It's much more interactive, I think, to do it this way. I know, but that's just me. Okay, questions with this one. This would basically kind of be like a problem in the exam. And I'm going to give you guys some exercises to do. That's going to be the next homework task, and you should be good. This learning module isn't going to be as intense as the other ones, because again, what's going to be a little bit more intense with these are the methods. There are other methods derived from this, which is the mesh method, the node method, the superposition method, but we're going to see those next. We're going to see those next semester. Okay, questions with this one? Okay, let me save this.